At the end of part 1 of our lecture on the evolution of high-mass stars, we followed the evolution of a high-mass star from stellar birth until carbon fusion was exhausted inside of the core. If the star is between 4 and 8 times the mass of the Sun on the main sequence, this is the end of the star's life. The inert oxygen-neon-magnesium core continues to collapse but never gets hot enough for subsequent fusion. As a consequence, the envelope is blown off in unstable thermal pulsations, and we are left with an oxygen-neon-magnesium white dwarf, terminating the life of a 4 to 8 solar mass star. We're now going to follow the evolution of a high-mass star with a mass exceeding 8 times the mass of the Sun. If the star's mass exceeds 8 times the mass of the Sun, the star will continue evolving very rapidly at the end of the carbon fusion stage. The core evolves so rapidly during this phase that the huge extended envelope cannot keep up. Recall that the cool envelope during this final red giant phase extends out to about 5 astronomical units, about the distance of Jupiter from the Sun. As a consequence, this very large ball of gas only responds fairly slowly to changes going on in the deep interior. There may be some outward manifestations of the processes that I'm about to describe, but probably only during the last few phases when there are numerous nuclear fusion shells. For the most part, the star is going to continue to get most of its energy from the fusion of increasingly heavy nuclei inside of its core. This core nuclear fusion is going to be able to keep the star in a state of thermal and hydrostatic equilibrium for a little bit longer. But this process comes at an enormous price. Each new fusion source the star will begin to tap in order to make up for its enormous energy needs is going to be more inefficient than the last one. As a consequence, each of the subsequent phases of the star's evolution is going to proceed faster and faster until it's moving so fast that it actually can take me longer to describe it than it actually has to occur. So let's now follow the evolution of a star exceeding 8 times the mass of the Sun from the end of the carbon fusion stage forward. In this case, I'm going to choose as my reference model a star of approximately 15 times the mass of the Sun. This is going to call upon the best state-of-the-art calculations of the evolution of a high-mass star. Now, bear in mind some of the details may in fact change as we learn more about stars, but the basic picture is the same. It's a pretty interesting story, and it happens pretty fast. So let's go. We leave the star at the end of the carbon fusion stage with an inert oxygen and neon magnesium core. As we've seen before, this inert core is not hot enough for its own fusion, so it begins to collapse under its own weight. As it collapses, it heats up, getting energy from the Kelvin-Helmholtz mechanism. This heating continues until the oxygen neon magnesium core reaches a temperature of approximately 1.5 billion degrees Kelvin. This is the point at which neon fusion ignites. The core density at this point is enormous. It's about 10 million grams per cubic centimeter. Neon fusion is a nuclear fusion reaction network. The two main products of this nuclear fusion reaction network are oxygen and magnesium, plus a number of other heavy nuclei. This oxygen and magnesium is the primary product and quickly builds up an inert oxygen-magnesium core, adding to the oxygen and magnesium that was already there from the previous carbon fusion stage. Neon fusion produces an enormous amount of neutrinos, so many neutrinos that the losses due to energy due to neutrinos exceeds the star's luminosity. Imagine, for example, that in a particular star, neon fusion produces, say, 10 times more energy in neutrinos than it does in photons. This would mean that those neutrinos, since they simply stream out of the core, out through the envelope, and carry that energy away from space, are putting energy into a form that does not contribute to the star's luminosity. As a consequence, the nuclear fusion has to run at a simply furious rate because it's producing so few photons that can provide for the star's enormous luminosity needs. Remember, at this phase, the star is a very luminous, hot red supergiant star. As a consequence, Neon fusion does not last very long. In a star of about 15 times the mass of the Sun, neon fusion can only last for about 5 years before core neon is exhausted. When core neon is exhausted, this inert oxygen magnesium core that has been building up over the last 5 years, well, you can guess it, it becomes unstable against gravity and it begins to slowly contract and heat up. This contraction and heating continues until the oxygen magnesium core reaches a temperature of approximately 2.1 billion degrees Kelvin. At this phase, we have an oxygen core surrounded by a neon fusion shell, surrounded by a carbon fusion shell, surrounded by a helium fusion shell, surrounded by a hydrogen fusion shell. The temperature of the oxygen core at this point is a few tens of millions of grams per cubic centimeter. Oxygen fusion is a furious nuclear reaction network that produces as its primary product silicon, with a little bit of sulfur and phosphorus, plus other nuclei, quickly building up an inert silicon core. The neutrino losses during oxygen fusion are simply enormous. Neutrino losses exceed 100,000 times the luminosity of the star. The star's luminosity is already huge. It's probably a few 100,000 solar luminosities as a red supergiant. As a consequence, it's producing 100,000 times more energy in neutrinos, which are just streaming away from the center, than it can produce to make up for all the photons being lost from this 100,000, nearly million solar luminosity red supergiant. As a consequence, oxygen fusion has to burn at a simply prodigious rate, so fast that core oxygen fusion will exhaust all the available oxygen after only 1 year. What does the silicon do? Well, the silicon's been building up in the core. Eventually that silicon core becomes unstable. As the silicon core becomes unstable, it begins to contract. As it contracts, it begins to heat up. Silicon core will continue to contract until it reaches a core temperature of approximately 3.5 billion degrees Kelvin at a core density exceeding 100 million grams per cubic centimeter. At this point, silicon fusion ignites in the core, is surrounded by an oxygen fusion shell, which is surrounded by a neon fusion shell, which is surrounded by a carbon fusion shell, which is surrounded by a helium fusion shell, which itself is surrounded by a hydrogen fusion shell. All of this embedded in a cool extended envelope that extends out to 5 astronomical units. I haven't even drawn the envelope to scale. This whole network of interlocking shells is barely bigger than the Earth, and the shell itself extends out well to the orbit of Jupiter around the Sun. So at this point, we're talking about stuff going on deep, deep, deep inside the interior of this red supergiant star that has no idea what's coming. Silicon fusion is the most complex nuclear fusion reaction network of all. In some sense, the silicon practically melts into a sea of helium, protons, and neutrons that begins furiously fusing, building up heavy nuclei until it produces as its primary end products iron and nickel atomic nuclei. It's not hot enough for iron or nickel to undergo further fusion, and so this iron and nickel forms an inert iron-nickel core. This iron-nickel core grows extremely rapidly to about 1.5 times the mass of the Sun, and it does so rapidly that the star exhausts all of the silicon available for fusion in its core after only 1 day. The star is now in trouble, but let's see where we've come. When the star was on the main sequence, it could burn hydrogen into helium through fusion to provide for all of its energy needs for a few million up to about 10 million years, depending upon its mass. When it ran out of core fusion, the helium core contracted until helium fusion ignited. When helium fusion ignites, it can provide for the star's energy needs for about 1 million years. But even then, helium can't last forever. The carbon-oxygen core collapses. Carbon can fuse, but carbon fusion can only provide for the star's luminosity needs for about 1,000 years. This is followed by neon fusion, which lasts for about 5 years, oxygen fusion, which lasts for about 1 year, and now silicon fusion, which only lasts for 1 day. To this point, the star has been generating energy, making up for its luminosity losses at its surface, and keeping itself in thermal equilibrium by making up for each and every lost photon with nuclear fusion. It does this by fusing light elements into heavier elements, tapping into nuclear binding energy. This diagram on this page is the curve of nuclear binding energy. It shows the average binding energy per nucleon inside of the nucleus as a function of the number of nucleons, protons or neutrons, that are found in the nucleus. The higher the binding energy per nucleon, the more tightly bound the nucleus. As we go from light nuclei like protons, deuterium, light and normal helium, all the way up to heavy helium-4, and then up to carbon, oxygen, neon, magnesium, and silicon, we are growing into nuclei with increasing nuclear binding energy. But notice the size of the jump. From hydrogen to a helium nucleus is an enormous jump in the amount of binding energy per nucleus. Not surprisingly, the nuclear fusion yield, from hydrogen fusion into helium is enormous. So enormous, the star can keep its energy needs up for millions of years. The jump from helium to carbon, however, is smaller, approximately 1/10 of the jump from hydrogen to helium, and so as a consequence, the helium fusion phase will only last about 1/10 as long, or less, than the hydrogen fusion phase. The jump from carbon to oxygen is smaller still and lasts for only about 1,000 years. While this jump looks pretty big, remember it's abetted by increasing neutrino losses. And so while we have a pretty good-sized jump from carbon-12 to oxygen-16 for fusion, this jump is offset by losses from neutrinos. And as we went from carbon fusion to neon fusion, then oxygen fusion, then silicon fusion, we're slowly but surely building up towards iron and nickel. I've shown the peak here near iron. At iron and nickel, the curve of nuclear binding energy reaches a peak, and with subsequently heavier and heavier nuclei, going all the way up to uranium-235 and 238, the heaviest naturally occurring nuclei that we find, all subsequently heavier nuclei have less binding energy than the previous light nucleus. So this tells you the physics of nuclear fusion is about to change. For the light nuclei, from hydrogen up to iron, nuclear fusion generates energy. Each fusion of a light nucleus into a heavier nucleus results in a more tightly bound nucleus and the release of nuclear binding energy. However, for nuclei of iron and nickel and heavier, fusion gives you lower energy. So therefore, fission, breaking of a heavy nucleus into two lighter nuclei, is the only nuclear reaction that will liberate or generate energy. So as a consequence, the fission or splitting of nuclei heavier than iron and nickel will release nuclear binding energy. This tells us if some process occurs that causes light nuclei to fuse into heavier nuclei, heavier than iron and nickel, this fusion of heavy nuclei is not going to generate energy, but is going to take energy away from the star. And this is the essential crossroads that a massive star finds itself at the end of the silicon fusion stage. By the time that it builds up an inert iron-nickel core, it has simply run out of available nuclear fusion fuel. Any subsequent nuclear fusion reaction is not going to make energy, it's going to take energy. When silicon fusion runs out, forming an inert iron-nickel core between 1.5 and 2 solar masses and roughly the radius of the Earth, the star is now in trouble. When nuclear fusion is exhausted, it's got a 1.5 to 2 solar mass iron-nickel core sitting in the center, surrounded by a silicon fusion shell, surrounded by an oxygen fusion shell, which is surrounded by a neon fusion shell, which is surrounded by a carbon fusion shell, which is surrounded by a helium, and finally a hydrogen fusion shell, all embedded in this enormous, fat, extended 5 astronomical unit envelope. At this stage, the core density exceeds 10 billion grams per cubic centimeter and a core temperature of 10 billion degrees Kelvin. But because the inert iron-nickel core is at the top of the curve of nuclear binding energy, there are no more fusion sources available to it to create more energy. Only the remnant fusion going on in a progression of increasingly unstable shells. The inert iron-nickel core grows in size until it becomes unstable and it starts to collapse under its own weight. But this time, the story is different. This collapse, unlike all the previous collapses that have occurred, is not going to be followed by the ignition of yet another heavy nucleus nuclear fusion reaction, because there are no heavy nuclear fusion reactions left in the periodic table. This time, the collapse is final and it is catastrophic. And we will look at the consequences of that in the following lecture.